All right, let's get into gear. Any questions for the notions of time and embedded and embodiment? You followed so far? Okay. I would like to use the approach by a colleague from the robotics community, Rolf Pfeiffer, from Unit Zurich. And he defines the term of embodiment in a very practical designer context by means of you need to have an operational environment which is supportive for your task. Sounds a bit weird that you do require that your operational environment in which you design your system in has to be supportive for what you want to do. Can you design a system in an environment which is unsupportive? Can you design a machine which is meant to pick flowers and deploy it in the middle of an active volcano?
You can't design it.
Yeah.
It depends on how unsupported it is.
Yeah.
You know, like the real world isn't totally supported on the CPU or whatever.
Okay, I have to refine then in that case the term supportive. If you want to operate in your environment, you need to be able to interact, to sense your environment. If your environment doesn't allow you to sense what you need to get from your environment, you cannot operate and do a meaningful task in this environment. If, for example, you have not the means to measure temperatures in a few thousand degrees and you're in the middle of a volcano and you want to do a weather forecast and find out what environmental conditions there are, you are in the wrong environment. You cannot operate there. And it's more than that, because you need to design your system as actually a part of this environment, as part of this whole system. You have to be aware that your device will automatically become a part of your operational environment, so you have to design it from scratch to become this part of your environment. I think you realize that already by now. If you want to move fast with your environment, you need to be aware that all your memory, all your systems which you have at your hands to implement your system have to be able to survive this kind of environment. You need to be able to pad them accordingly to cater for shock waves going through your system, for example. Yes, some people like the challenge and you want to be in an environment which is giving you a bit of a challenge. Doesn't mean it's completely unsupportive. You will be able to connect with it on one level or the other. If not, your system is not working. If you're staying completely isolated from your environment. You get what I'm trying to say? Okay. And then it has to be a task, which means that any kind of a sensible embedded system has a task, is situated, is obviously embodied, and is self-sufficient to some degree. Why is embodiment important? Can anybody answer that? Can I leave embodiment out of this? Yes, that's. But if you leave embodiment out, what does it mean here concretely to build and design a system?
It's not properly part of the environment.
Yes. What can you no longer do?
Build or interact with the environment.
Yeah, you cannot sense anything. You cannot do anything. You cannot have any effect. So you need a body to sense and to interact with your environment. And that also addresses the question which we had a few slides earlier about can you build an intelligent system, which is an abstract thought, an abstract idea. And you build this without any interaction with your environment. Okay. So this all goes to what you see more and more in most robotics designs these days, that you have such a tight coupling between perception and action, interaction with your environment, that the line between perception and action is becoming quite blurry. You cannot do one without the other. If you have a pure one-way system, you will have trouble defining that in the first place. You saw this in the case of all the sensors which we had so far. Sensing something without changing it is really, really hard. Okay. So if we do this under real-time constraints, that's obviously becoming a real-time system. And if we construct any kind of a meaningful morphology, that's called an embedded system. Why is designing a meaningful morphology a challenge? Isn't that obvious? Can you always design easily a meaningful morphology?
What's morphology?
A morphology is a physical placement of things. So morphology means that you design, for example, a robot, and the choice where to place the wheels or the legs or whatever you have for interacting is a morphological choice. So your body is a morphology, and the design where you have your arms and where you have your ears and where you have your eyes is defining your morphology. And that design appears often obvious, but is often anything but. How do you design, for example, a robot which is able to traverse terrain which is extremely rocky? Or you have stairs, and you want to have a camera on that thing.
Helicopter blades?
Yeah, you don't touch your environment in the first place, you just stay over it. What if you have to survive there for a week?
Land a lot.
Land a lot? Okay. So you design a helicopter which is able to land on rocks?
Yes.
Yes. You make this sound easy?
Yes.
Well, obviously this is hard. If you have rough terrain, you have to consider the possibility that you fall over, you tumble over. Can you build a morphology which can fall over without damaging itself or becoming unmovable?
You basically made like quadruples that are encased in a spherical, like kind of roll cage type thing. It self-balances itself, so it's always facing up.
Mm-hmm. Okay. So balls often come to mind. And yes, this has been done many, many times. That you just build a flying vehicle of any sort. This has been done for, I think, pretty much any flying vehicle I've ever seen. That at some point people came up with the idea that flying vehicles are kind of dodgy because they can fly into stuff. And when they land, they often cannot take off anymore because they land and they fall over. So the obvious solution is that you just put this in a sphere and make it self-balancing inside a sphere. I've seen quadcopters for that, or hexacopters. I've seen whole helicopters being put into one of these things. Yeah. It hasn't really taken on to do that. In limited applications, I'd say this has been successful if you want to, for example, fly indoors with extremely lightweight vehicles, and you know that bumping into stuff is usually taking you down as a flying vehicle, so you try to have some kind of bumpers around it. The problem with bumpers is, A, they're big, So you have to actually, you increase the size of your vehicle in the process, which makes it impossible to go into the places where you wanted to go in the first place. Slight drawback. And it increases weight. And flying vehicles and weight is usually an issue. Okay, you can use carbon fiber. Lots of carbon fiber. Very thin carbon fiber. Yeah, but very thin carbon fiber also breaks very easily. So, yeah.
Adjustable wheel alignment, so you can shift the height of the wheel.
Adjustable wheel alignment.
So you can flip over, you can adjust it so it flips back because of the weight alignment.
So if your vehicle lies on its roof, you just move the vehicle to the other side. Okay, and if it lies on the side,
you keep it so the weight balance is so much greater on one side, so it has to flip over.
you just wiggle until it falls over again. Huh?
Yeah. Well, do you use them as a wheel alignment, so make one wheel so big?
So put a cage around it and an arm and movable legs. It's all becoming very easy.
Build it with 4 wheels, in first 3 in a triangle, and then the other one in the butt.
Okay.
Have
So
it directional.
let me give you a bit more of a challenge. We're only talking about legs so far and wheels. You want to have this thing equipped with a camera to give the operator some kind of an idea of what's going on as well. Where do you put the camera? I mean, without the operator vomiting all the time. So.
Put that inside a little cage.
Just tie it to a spring so it's always down.
Okay. And then you want to measure the temperature. Very simple. Where do you put a temperature sensor?
Not next to the heatsink.
Not next to the heatsink. Okay.
Unless you want to measure the CPU temp.
Now I want to measure the temperature of the ground underneath me.
Probably near the ground.
Very near the ground. But we don't know where the ground is because you said the ground could actually be on the roof. So
Laser thermometer.
just.
Infrared camera.
Okay. So then you want to have the sensors in a way that they don't get ripped off the whole thing all the time. Okay. So this is now a big blend about robotics design and custom design for consumer devices. And these questions are important, where to put your sensors, because it defines what you can actually do, what this vehicle is able to interact with its environment. It's not a trivial task at all. Okay. Particularly for you as you want to design new stuff, not just reproducing what is already there. If you want to invent something new there, these things are anything but obvious. So, enough for the general concepts of time and embodiment. I just wanted to raise these topics as a general topic first. And now we can go into doing it concretely. So let's start small. Interfacing with time. Interfacing with time. First job, you want to find out what time it is. We already discussed about the principal ability of finding out what time it is, or the principal limitations of trying to find out what time it is. It's not obvious that you can't do this in the first place. But let's look at it from different programming language environments. Java, real-time Java, Ada, POSIX, BARC. What do you have there? And I categorize that just in what is the resolution in terms of syntax, what is the required range of these time expressions, time instances which you have there.
What do you mean by
Required range. If you define a variable which can carry time, and then you make this go, let this roll, how long does it take until it overflows? So what is the persistence, the range of this instance? And this is usually undefined. In hardware timers, you have a very clear perception how long it takes to roll over. If you do this from higher level programming languages, usually you don't have an actual definition for that. It's machine dependent, compiler dependent. You have to look it up somewhere in the manual. With the only exception of Ada, which actually requires that the range has to be 50 years minimum. When you define a time variable and you let it go, it has to actually take at least 50 years to roll over. Then required resolution and the actual resolution, because the required resolution is only the bare minimum, what the language requires you to implement as a compiler constructor. But the actual resolution is usually way higher than this, because technology progresses, and this is only the syntactical minimum defined. You have a language guarantee position in POSIX of 20 milliseconds, in Ada of 1 millisecond. In both cases, hopefully, the actual resolution is way finer than that. And the important part is not the required resolution, but can you actually detect the resolution which is on your system? If you start up your system, can you detect what the actual resolution will be? And this is also defined as you can check this in POSIX or in Ada or in real-time Java. And on hardware timers anyway, C has a stunningly little standard for time definitions. You have some integers counting up from Unix boot time. This is basically what you have in those environments. Okay. We'll discuss a lot about software timers and hardware timers in a moment. So syntactically, you will see this one here a lot. This is your simple interface into Ada real-time, often also referred to as Ada or monotonic time. Monotonic time, obviously, because the one guarantee you have on this time, which is important, is it will not ever go backwards. This is guaranteed to be a monotonic time. And also referred as real time. So you have definitions of a tick, which is your actual clock resolution, which is just simply a constant, obviously, defined on your concrete implementation of what you have. And then you have a function clock, which returns time. Surprise. What time is, you don't get told here, but you can actually then use and operate on time in any way you want. Okay. The other interface which you have in Ada is the interface which you probably will not use in your work here. This is Ada calendar time. Calendar time is what you use if you want to find out what day of the week it is. But you have to be careful because calendar time can go forwards and backwards. So in real-time environments, you're very rarely referring to that unless you actually need to know what day of the week it is. So this is the interface just reading time.
If your programs to operate, like change the time zone, like what the time zones you're in,
Yeah.
would you use Ada real time or would you use calendar time since this can't go back?
Well, the concept of time zone means against notion of solar time. Real time doesn't have anything to do with that. So in that case, you usually have both of these things in parallel, that you have solar time for references of your time zones or your geographic location or something like that, and you have real time for your actual control applications. Nobody stops you from having these both of these notions of times concurrently. And then you have the package real-time timing events package. That gives you access to hardware timers. Not on your lab computers, but on embedded systems you have that. Because those handlers are directly going onto your hardware timers. Obviously, if you run on Windows or on Linux, you do not have any kind of access to hardware timers. Not to talk about the fact that your lab machines don't have any hardware timers to start with. Even if you would have an operating system which would allow you to do that, you don't even have the hardware to do that. That gives you the possibility to nail down events which are hard connected to timers and directly activated when these timers are running out, without any scheduler in between or any other tasking synchronization process happening in between. So this is hard. You're ripping out any kind of synchronization mechanism which you may have otherwise in your tasking system. This is beyond that. Do you have a decent understanding between the difference of scheduling and changing contexts on a tasking level, on a process level, as opposed to changing context on an interrupt level on the hardware level. Do we have to address that?
Do interrupts actually cause a context switch or not necessarily?
Do interrupts always cause a context switch?
Depends what code you write. You know, the interrupt handler.
Exactly. If your interrupt handler is a dispatcher or a scheduler, then you probably want to change context. But an interrupt handler is in the first place a bunch of code which can do anything. And your interrupt handler is the important thing. At this level, the interrupt handler has, in the first instance, absolutely no notion of processes or schedulers or anything like that. It lives in a different universe from your processes. Is that so far something you're familiar with? Who has actually programmed interrupt handlers? Well, everybody who has seen 2300 obviously has used interrupt handlers. The engineers are still a bit virgin on that side. You have not used actual interrupt handlers? Second?
I did 2300.
Yeah, okay. Okay. We'll talk about this a little bit to some degree, but a general understanding of the difference between processes and handling direct interrupts is essential to understand quite a bit of that. But ask questions if something is not quite clear. Okay. I will give you some diagrams which actually make it a bit clearer in a moment. Okay, I would like to skip the real-time Java stuff. This is what it looks like in POSIX. And this is not monotonic time, obviously, because you have a function which is called set time. Gives you all possibilities. You can do what you want here. And you have a sleep operation which gives you a callback once this is done. Whether this is going to actual hardware timers or not, you don't know. That's not really defined here. So if you call delay, as you have already done, in your programming environment, or sleep, or whatever it's called in your language, how long will you knock out this process? I say sleep 1 second, or delay 1 second. How long do you actually knock out this process?
At a minimum 1 second?
Yeah. At a minimum of 1 second, plus context switch, plus.
Also, plus when it gets, if this is not a real time, that would be real time, but when it gets given priority again.
Okay. So not only plus context switch, but plus there could be something more important running right now. So you say delay 1 second. That doesn't mean that in 1 second from now, you're the most important task in the system.
What if you were just using the CPU calling delay?
This is not calling delay. So this is you not actually surrendering anything to your environment at all. So if you say delay, this is suspending the current process, entering something into the scheduler, the timer, which wakes the scheduler up at a certain time, maybe, if the priority is right. And then there are a number of other effects which will delay you further. First one is simply a granularity jitter. Maybe you express the time in which you want to be delayed to a granularity which is beyond what the system can exactly express. There's a lot of things which define this granularity. That's the timer itself. It's simply the CPU's clocks, etc., etc. So you always have a base granularity. This base granularity is always added regardless of what you do. Then, well, the interrupts could currently simply be physically disabled. So it doesn't help you much to have set up your kitchen timer to be woken up again after a certain period expires. If your interrupts are disabled at this time, absolutely nothing is going to happen at this point in time. Right? So that's the first phase. You have to wait until interrupts are coming up again. that you can go through. Then, when your interrupts are enabled and your specific interrupt priority is enabled, because interrupts have priorities as well, as you know, and then you start your interrupt routine. And if this interrupt routine has anything to do with the scheduling and the delay operation here, then your task switch is being initiated. And you have to go through the task switch, the context switch, and you wait. Then you actually only enable that. And then you have to wait on the next level, so to speak, on the scheduling level, whether your task has the right priority at the moment to run.
Can you guess how long that takes and just subtract it from the time you have to delay for?
Can you estimate, you mean the whole delay here?
Yeah.
Can you estimate this whole delay? You couldn't? You could? You could do a worst case? You don't care, really. Okay, so we pretty much had the full spectrum between yes, no, maybe, don't care. Would it be thinkable to estimate that? How many things do you need to get under control? Okay, I have only one task in the whole system, which means I have no trouble with interrupts, no trouble with priorities anymore. I know that my system, my scheduler, will idle and stare at this timer all the time anyway, because my system is going to get bored. There's nobody else there. Okay, so I can make a lot of assumptions, and then eventually can get there. But that also means you do not have, for example, any other timer interrupt, any other interrupt routine running on your system. That could be rare, that you have actually only a single timer interrupt you're waiting for and nothing else.
Make the timer interrupt have priority over the other ones.
Yeah, which of your 5 timer interrupts do you have priority?
The
The one
one
which is important for me. Exactly. And if I'm designing my whole system like that, so there's only one timer interrupt, there's only one task, there's only one interrupt priority, why do I use the interrupt in the first place? Right? So to come back, in practical terms, no. If my system is so exotic that I could do that, I probably wouldn't use a delay operation in the first place, because then I can use my CPU to stare at the clock anyway. I don't need to have that kind of estimation. Okay. The effect between the intended delay and the actual delay is called the local drift. And whether you can estimate the drift or not is one question, but usually you have to acknowledge that there is a drift in this kind of environment. This is the important part. And then you can compensate for the fact that there is a drift in the first place, and you want to make sure that your drift is not accumulating, that your drift is not leading to an overall drifting away of my system, but you can set this back, you can compensate for that. Yeah?
What kind of drift would you reasonably expect in, just like a few examples?
There is no number which I can give you for that. It so much depends on your actual environment. This could be anything between microseconds and weeks, depending how you design your system there. Now, here you see the difference if you actually work on hardware timers, as opposed to working on a scheduler environment. If you work on hardware timers, then the actual delay is counted until your interrupt routine is activated. And your scheduler doesn't play any part in that. Okay, so you cut out a lot of the delay if you go to a hard timer, as opposed to a language-defined sleep or delay statement. Okay. Which means, now very practical, if you write something like this, something has to happen, then you put yourself to sleep for 5 seconds, something has to happen again, I put myself to sleep for 5 seconds. You could program it like that, right? No, you couldn't. That's a statement which you see on the screen here, which is mostly forbidden in real-time systems. Why?
Because like after it's run 100 times, it's very likely that you're not going to be near 500 seconds.
Yeah, because the obvious, usually underlying assumption here is that you do something every 5 seconds. Now, if you want to do something every 5 seconds, this is a guarantee to failure, what you have on the screen here. Because A, you don't know how long action takes, unless you solve the halting problem. And you already know that the delay statement will be more than 5 seconds anyway, under all circumstances. It will always be more than 5 seconds. So even if delay is completely predictable, even if action is completely predictable, even then, this is a silly way of expressing it. So what you do instead is you use a delay until, an absolute delay statement. And hence, in pretty much all real-time systems, you have only absolute delay statements. You never have relative delay statements. An absolute delay statement enables you to say something like this. I want to start at the current time, and I want to set myself my kitchen timer to the current clock plus the interval, which I defined as 5 seconds. So independent of how much time already progressed, I will now set the next time to a sensible value. And I can now have, throughout a minute, every 5 seconds, an activation, regardless how long action takes, regardless how long my delay statement actually is. Yes, I cannot avoid the local drift. So this has also a local drift effect. But it doesn't accumulate anymore. Is that obvious? You look a little bit worried. Not that obvious? Okay. What happens if action takes half an hour? Then you?
Delay would basically be, would it be skipped, or like it would do the equivalent of like, well, if your delay is 0 on either, if like it's in a scheduled environment, it just goes to anything else in the schedule.
Mm-hmm. If action actually takes a lot longer, that means my next delay until statement will be in the past. Right? If you have a delay until statement which is in the past, it means don't delay. Because I'm waiting for 1 o'clock in the afternoon at past, so I don't delay. It's identical to a delay 0, which means that you still can provoke a task switch on the same priority level. For completeness sake, we'll see what this means later here.
So is that kind of the equivalent of a lecturer saying, I want this on my desk yesterday, meaning like you better freaking work as fast as you can and get it there, and maybe I'll thank you, but maybe I won't.
Yes, thanks for the metaphor. Yeah. Okay. And this can happen then a number of times. So if action overran once significantly, then for the next 5 times, the delay statements are actually not delay statements. It just runs through directly until it begins to catch up again. Of course, if delay is always larger than 5 seconds, well, then you don't stand a chance. But this has nothing to do with the delay statement. But if you have a loop when you want to do something every 5 seconds, and you know what you want to do is always taking longer than 5 seconds, you are kind of doomed. Okay. So, can I emulate that? If I have a system at my hands which only gives me a relative delay statement, can I do it like that? That wouldn't be so bad. So that's not the reason. In I have a negative delay, it's also not delaying, yeah?
Because you're taking your start time at
Yeah.
the beginning of the loop,
Yeah.
and you've got your accumulated delay after your delay statement, which is not accounted for. So like when you
Okay.
finish the delay statement,
Yeah.
there's
Yeah.
some time before you actually execute the next instruction.
Mm-hmm. Mm-hmm. Yeah.
So you're not accounting for that time.
Mm-hmm. Mm-hmm.
Could you effectively do it by every time, like your delay for interval minus, well, that for the first time, but then your new clock equals the current time minus the interval minus the start time. So basically you have like, you know how long it delayed for relative to how long it actually delayed for.
Let me give you a hint. Think interleaving. You're not the only process on the planet. Which means that this process here can be interrupted anytime. If you can be interrupted anytime,
So does that mean that it actually is finished, but it is interrupted, and then when you come back to the delay statement, the clock is actually so it's still accumulating delay, right?
the statement interval minus clock minus start time can be interrupted 5 times. Which means the actual clock which you read there is irrelevant. Right? If you need to have an absolute time statement, you need to be sure that when you actually call the delay, you have an information what my current time is. With an absolute delay statement, you can do that. With a relative delay statement, you don't stand a chance.
But even if there was no interrupts, this still wouldn't work.
It would still be dodgy.
Well,
Even if there's no interrupt, it still wouldn't work. Okay?
so say your delay statement can take any length of time. Right?
Yeah, yeah.
So say it takes 10 seconds,
Mm-hmm.
and then your start time does not account for that.
Yes. So even then it would actually be dodgy. Yeah. And in principle, even if you compensate for that effect, you don't stand a chance, because unless you have some atomicity in your timing expressions, you know that when I calculate my next time, I cannot be interrupted during this calculation. So the time between reading my clock and calculating the next time is uninterruptible. Now, if that's the case, you do have an absolute delay statement. So nope, that's not going to work, because that's not working. You frequently see statements like this: sleep for no time, delay for no time. Quite common. What does it mean? Yes, it's a bit of a weird expression for yield. What does yield mean? I give up. I give up to whose benefit?
Another task.
Say again?
On the same priority.
On the same priority, right? Because you cannot give it up to the benefit of somebody on the lower priority. Can you give it up to the benefit of somebody on a higher priority?
They would have taken it already.
Okay.
So you had it or next to a mug, it's already taken the money.
Okay. So I can say yield. I have also the instruction yield to higher. So can I give it up to a higher priority now or not?
Because you don't task switch unless there's some sort of yield statement. So
That's not true.
is that not?
That's not true. That's not true. If the higher priority becomes runnable due to an external event, because the higher priority has been waiting for an interrupt to happen, has been waiting for I/O to happen. As soon as this I/O happens, the higher priority task will be activated. So yes, there need to be some interaction points in my overall system, but you don't have to yield to make this happen. Which means that in a real-time system, you always have to be considered you will be rudely interrupted as a lower priority task by a higher priority task anyway. So what's this yield to higher than supposed to be?
I guess as it says there, it works with a non-preemptive scheduler. So if you're using, if something if a higher priority task gets created, it might not necessarily start running until something queues.
Yeah. So two possibilities. Either you don't have a preemptive scheduler at all, and there are sorry, I have to correct this one. I said in the previous sentence that you always have to consider the fact that in a real-time system you have to be interrupted. There are even harder real-time systems which do not have preemption. And in those environments, yes, you do need to do this explicitly. And if you're working on the other side of it, that you don't have a real-time scheduler in the first place, but you have some kind of a mixture between priorities and round-robin Linux, that you need to explicitly say that you want to actually yield to a higher priority task, because this is not happening automatically in all environments. Okay. This is a bit exotic in real-time environments, unless you actually have a non-preemptive scheduler in your system. You can choose between a whole bunch of different schedulers in your Ada runtime environment. The mandatory schedulers we talk about later. What you usually have in all real-time environments is a fixed priority scheduler. But there are a bunch of other schedulers which are available to you by different language environments. So Ada, as I said, comes with a number of different ones. So as opposed to delay statements, if you use actually a timer event, timers can also be set relative or absolute, and same things apply, only that here you cut out all the tasking. This is a protected procedure as opposed to a task. Interrupt routines always have to be protected procedures. Can you imagine why? Speak a bit.
It's probably unsafe.
It's probably unsafe. Yeah. If it's not like that, why is it unsafe if it's not a protected procedure?
Because if one of them starts running and then an interrupt calls the second instance of the same procedure, you could be
Isn't that what maskable and non-maskable interrupts?
Yeah, you can do this with most interrupts. You can interrupt yourself. Okay. It becomes a little bit more fuzzy why you want to have a protected procedure.
Because you can interrupt
any other task or whatever. So you don't want to access memory or something that task might use.
Yeah, it just already gives you a very comfortable handle to protect some data, which you want to keep away from everybody else. So you can define your interrupt handler as this is some data, some space where your interrupt handler can work without messing with anybody else. And same thing, you can also set this to absolute time by giving this, well, simply a parameter which is absolute time. So absolute and relative delays are available in most environments. You go down to only absolute delays in all strict real-time systems. Your system qualifies as strict real-time, which you will be working in, because you will be working in Ada Ravenscar directly, so you don't have access to relative delay statements at all. Will all be absolute delays anyway. And in some environments, you actually only have relative delays or timers, which is POSIX.
Can you get much stricter than strict real time to get any better?
Much stricter than strict
Is
real
it as
time?
much as you can go without it not really helping?
No, we talk about this in a moment. Strict real time can become very, very, very strict. So there are different gradations of strictness. Yeah. Okay. So after we finally were able, yeah.
You mentioned in the previous slide that event handlers were more precise. Why is that?
That event handlers are more precise
Yeah.
because they are connecting to individual hardware timers. If you use the delay statement can only be used for you as a task. You have no possibilities to use a delay statement in the philosophy of an interrupt handler. A delay statement means your task, your current process, is being delayed until something happens, which means that you need to have a context switch. You need to have a scheduler. Here, you have a routine which is called your timer routine, which is a procedure. And this procedure, the address of this procedure is hard written into the interrupt vector table of your CPU, of your machine. Then this interrupt vector is associated with this hardware timer, and this hardware timer triggers, this interrupt routine comes up. Hence, it's way more precise than doing this via delay statement process level. Yeah.
And you're announcing as active part, so does it mean this handle cannot be interrupted by any other means?
This depends on the definition of priorities of your system. We'll come to that a little later.
But it's protected part, and during the protected procedure, it's supposed not to be interrupted.
Not on the same level, yes. Yeah. But a little careful here. That's not necessarily God-given here. Goodie. So, after we find out what time it is and we can delay, the next thing is you want to be able to define timeouts. When do you need timeouts? Whenever you want to wait for something. You want to make sure that you're not waiting for forever for any kind of blocking operation, but you can associate timeouts with whatever you're doing. The two first ones are quite obvious: timeouts on synchronization primitives and timeouts on message passing. Timeouts on synchronization primitives is if you call wait on a semaphore or you call a protected object, how long do you want? Are you prepared to wait if you're not getting through? Timeout on message passing, you want to communicate with another machine and you want to put a timeout on that one. Classically, you have any kind of a network interface, any kind of synchronous message passing. You are only prepared to wait for a certain amount of time. If this thing is not coming up, you do something else. The last one is a little bit more tricky and something you probably have not used so far in your career: timeout on action. That means that you're monitoring yourself, your process all the time. You say you can execute a statement block. You start executing sequential statements in your process, but when you start doing that, you're also setting yourself a watchdog timer on the side. If I'm not getting through this block of statements in a prescribed amount of time, you're interrupting this. You're ripping yourself out of executing statements, and you do something else instead. That's a style of programming which you're probably not used to yet. Say again? An abort is a method to, or usually what you say an abort statement in that sense. An abort is you're shooting somebody else. You take the shotgun out and you kill another process. You abort another process. Here you're aborting a part of your own process. which is timeout on action. Right? You will use that plenty, and this is something which is actually quite commonly used in real-time systems. Timeouts in POSIX, classical semaphore wait operation, and I have a semaphore timed wait operation. A little hint for using POSIX here. The classical way to find out what actually happened, for example, the fact that you didn't go through, but my semaphore timed out. The only way to know about this is by reading the global variable error number in POSIX. There's a C interface, right? You don't have any other feedback which you have here. You can only read this error number here. And as I said here on the slide here already, at this time it's a good time for decent prayer, because error number has to be thread safe. Does that make sense? Why do I say error number has to be thread safe?
Because if another thread happens to have another error before you handled the error number.
Yeah, in the naive implementation, in naive POSIX philosophy here, C interfaces, they don't have any concept of concurrency, which means that an error number is a global variable. Now, if you just have a global variable, you have been trying to do that, and somebody else has been using a similar interface which uses the same error number. You can read the other guy's error number, which is a bit confusing. Right? So fortunately, in most POSIX environments these days, they magically managed to make this global variable appear to be no longer a global variable, but actually working for individual threads. But better check that. Right? Because if you use a more low-level implementation of that one, that's not a given, that this is actually a thread-safe operation. So, otherwise, if you look at this kind of code, if error number equals God knows what, you probably start wishing for exception handling. And it's actually quite funny. What are people most whining about in industry when you have people working in C environments? This is the most frequent complaint which I hear from plain C programmers. Please give me some kind of exception handling. Because this kind of code drives you nuts and makes your code unreadable. And if you are working in a serious industrial system where you have large numbers of different errors and possibilities to check, this is much more code than your actual production code which you're writing there. And your error handling code is, of course, very error prone, which is kind of defeating the purpose. Okay, so exception handling is a good thing. Simple timeouts, as you can define them here. Timeout on outgoing calls, very simple. I have a select or delay with an outgoing statement, so I can now call on my controller to change something, and I will be patient for 500 milliseconds. After that, I will have to do something else. Okay.
So if the call has finished, it will still be running in the background?
No, the call is withdrawn. No. This is this can only work if your call has not been partially accepted yet. So the criteria here is, am I still in the waiting queue of this call? Which means I can cleanly withdraw without the other task or the other process or the other memory area noticing. You don't know what that controller is. It could be a protected object, could be a task, it doesn't matter. But you're still in a queue waiting to be picked by this other entity here. And then you can cleanly get out of this one after 500 milliseconds. If this controller accepted your task, but don't return, the controller doesn't release you. This controller just clamps you down forever. This doesn't get you out. Right?
There's a delay statement there, so will this text be swapped out?
Say again?
Will this text be suspended while I'm kind of waiting?
Yes. Yes. Well, first you will try whether controller is actually open right now. If controller is open right now, then you simply do the call and forget the whole rest of the select statement here straight away. Right? If your caller is currently not open and you end up in a queue, you put yourself into this queue and start your kitchen timer. Right? If you're being accepted before this timer expires, then you go through with the call, regardless how long it takes. We'll see other structures later where you can still rudely abort what's going on here, not with this kind of enterprise. This kind is a friendly timeout. Okay. And of course, usually you have an absolute deadline there, not a relative deadline. But otherwise, same thing. Or you're the really impatient kind of task, then you don't use a delay statement, but what do you use instead? Exactly. You say select else, do something else straight away. But be careful, because if you overuse that one, what kind of system are you producing? Exactly. You're just producing a busy waiting system very quickly. If all of your tasks are of the impatient kind, you can very, very quickly produce a wonderful either busy waiting system, that would even be the nice alternative. What's the worst thing which can come out of that? A live log. That everybody is spinning like mad, and you never get to an actual rendezvous situation. So you have two really, really impatient guys trying to exchange messages, and they're both constantly checking, is the other guy currently available? Is the other guy currently available? And they're never actually meeting, because they're both doing constantly something else, and rechecking always a slight few microseconds misadjusted. Actually, can you even ever get a rendezvous if both are doing that? Oh, you can't actually. No, in a multi-core CPU you could theoretically, but you need to be really lucky to actually hit them just at the right point that this actually goes through. So you will actually very quickly produce an actual live log system here. Yeah.
So in this instance, if your like series of threads was more like a server client,
Yeah.
like if there's one server providing, it was based on 5 other clients, and they're like, I want to be the first to do whenever I enter it, so I'll do stuff until it's available.
Then you're never getting through, because every time you go through this select statement here, you will start at the end of queue again, which means you take yourself out again. So your waiting time is not accumulating, and then you're never getting through to the server.
But like if the server's not going to have like 100% saturation time, if there's not always going to be a call being made.
Sure. Well, then you have to find the empty window where the server is actually empty. Okay. So obviously there are uses for those kind of statements. I'm just trying to caution you. If you use that, say, more than once in your system, you have to start thinking whether this is actually a good idea. If you use it once, it's usually okay. And you also use that server side. So you can also put timeouts on the acceptance side, not only on the sending out side. Select accept or delay, and then you can have, in this kind of environments, you can have many different delay statements and many different accepts at the same time. Yeah.
Would you ever do this though? Because if you
Yeah.
have the delay, you just go back to accepting. So just wait on the accept.
Well, there's a normal processing down there. So
Oh, right, sorry.
I assume that I have other hobbies as well on the server side, and then I can do my other hobbies and check back later. So I only have my office hours that I check for about 1 second at my door, whether there's actually a student there right now. And if there's no student there for 1 second, I go play for an hour, and then I check back again at my door for 1 second. So you wanted to have examples for lecturer environments to do that. So yes, this is definitely used. Okay. You can have also or delay something, or delay something else, or delay something else. You can have many different delay expressions here. Does that make sense? To have multiple lines of different delay statements? Say again? Exactly. So, of course, if I have only numerical literals with all the same form of delays, so I only have relative delays, and I have relative delay 1 second delay, 2 second delay, 3 seconds, that's of course silly. But usually you have a mixture of absolute relative delays, or you have, for example, only absolute delays, but a number of different deadlines which are all calculated live online. And it could well be that in some situation one deadline is earlier than the other, and in another situation the first deadline is earlier. So it does make a lot of sense, and you do see in practical systems many expressions where you have multiple different delay statements in a row, which, as I said, initially it looks a bit funny if you have multiple different delay statements, but that makes more sense. And of course, absolute delay statements as well. And you can also be a completely impatient server. So this is the lecture which is never available, because if there is not a student actually waiting in front of the door right now, you will never open. You will not wait for any kind of time at all. Okay, so this was the harmless, the nice way of timeouts. Let's get to the more real-time oriented way of timeout, the more ruder way of doing that. That's timeout on actions, or in more general terms, asynchronous transfer of control. You can now trigger actions inside your tasks which will make another task brutally change its sequence of operations. How does that look in practice? You can have something like this: select delay, then abort. Again, of course, with absolute or relative delays. What's the big difference to what we have seen so far? If you're not getting through with this initial delay here, which means you're not getting through because you have actually a delay statement here. You cannot execute this straight out. You will start your sequence which comes after the abort. This is the abortable part, the interruptible statement sequence. And you start executing this sequence of computation here. If you're getting through with those, you can complete your sequence of computations and you reach the end select. You made it. And you ignore everything else which was mentioned above in this select statement. Select statement is considered complete, and delay is withdrawn. If your delay hits you while you're still processing in there, you will be hard interrupted inside this statement sequence, and you will be kicked out to the end of the select statement straight away. Okay. I'm lying a little bit, because hard interrupted means that you don't have any non-interruptible sequences in there. So you can have non-interruptible elements inside your statement sequence here. You're not being kicked out of those. This is, for example, the case if you are inside a protected object at this point in time. So if you make a call to a protected object from inside this statement sequence, and you're inside a protected object right now, you're not being kicked out of that. This is considered a formulation of an uninterruptible statement sequence. You want to protect a certain statement sequence to be uninterruptible, you make this part protected, then you're not being kicked out of that, only at the end of it. Okay. So classical formulation. You can also do this, of course, on calls, not only on delay statements. Now I have a select and abort, which is dependent on a call to something else. If this call goes through straight away, I'm not executing any other code after the abort statement. If this call blocks you, you keep your business card in this call queue, but at the same time that your business card is lingering in this call queue, you keep running. You start all the expressions, all the statements which are coming after your abort here. If your call goes through, you're interrupting your own actions and you continue with the call. If you get your own actions through to the end of the select statement, you withdraw your business card from the call. Yeah?
Can you abort while you contact all agree about this, execute the end select? Like you add end select, you've done everything you wanted to do, but then the call goes through and then you abort.
Then I would use a different construct. If I don't have anything to interrupt here, then I use select or delay. If I want to do that differently, or select else, not a select and abort. So a select and abort is particularly meant to interrupt statement sequences. Or did I misunderstand what you're asking?
I think so. So the call goes through, and you were just about to execute your end select. Does that just get rid of everything you've done in the abort statement?
The call goes through, and you're just about to.
So you've done all the stuff you wanted to do in the abort section.
Yes, you reach your end select.
Yeah, and so you want to finish.
Yeah, then you.
The call goes through, and so you just abort the stuff you've done.
Well, yeah. Now you're talking about what is how fine-grained is that going to happen? Either you're actually getting through with the end select or you don't. So if you're getting to the end select, you're withdrawn here. You're talking about whether it takes time to actually withdraw this whole thing. This is not observable. It doesn't make any practical difference for you.
So the main question, only thing that you have to execute now is the end select. You haven't started. Mm-hmm. And that's call goes through. You just have to disregard everything you've done, even though you know the only thing that's left is to just execute the end select.
Hang on, you don't disregard what you have done. You're interrupting what you have done. So be careful. All the side effects which happen in this abortable part stick. So this is not undoing things. This is not a database interface. This is not a transaction operation. If anything has actually been changed in your memory in the abortable statement sequence, that stays. Hence, this is so nasty. This is actually aborting something in the middle of it.
Is it possible to have atomic operations within an abort statement?
Yeah, as I said, you can actually have protected objects, protected procedures, protected operations in there, which are defined as non-interruptible, and you're not being ripped out of the middle of those. So if you want to protect integrity of your data, that's one way of doing that, yeah. Yeah?
When you give another call to the block, so it blocks that one and then it resumes,
yeah.
and then goes to another block and it will execute the abort there.
Wonderful. This is what you will do in your labs this week. What you do in your labs this week, you have a whole cascade of select and abort statements. Yes, they can be cascaded, and they will be cascaded in practice. So you can be aborting a whole select and abort statement as well. Does that answer your question?
No, well, then you have to explicitly put another select. So.
Yes, I need to wrap this into another select and abort statement, yeah.
Yeah, but if the next line is just getting data again, like you just copy the first line twice.
Yeah.
And so it goes through the first call and then the second one. Then blocks.
No, hang on. The trigger is only the first call. No, I've misunderstood. What you were saying is if I have a number of calls here, the first and the second call have a very different semantic. Only the first call is a trigger for the select and abort statement. if I have a statement sequence after that which has other calls, this is all completely sequential again. So I have statement sequence which is possible after the first call, and this can be other calls, other select statements, whatever, but this is not interrupted. Once you get past this call, everything else just goes sequential after that. Let's look at this in a concrete example. Let's look at this as the actual code. Okay. Classical timeout on action. You want to improve something, get more precision out of your operation until a specific deadline hits you. Simply use the computational resource which you still have, iterate on your data until a specific deadline hits you. Be careful that you make sure that you take note when you reach the end of this whole operation. Or, typical case of sensor-driven processing. You have a select to a call which gives you access to new data from an outside sensor. And you make this call, receiving new information from an outside sensor, a trigger for an asynchronous transfer of control statement. What does that mean? It means that you have now your CPU available for any hobby you want, which is in the abortable part, where you can, for example, process the data from your previous readings. You can calculate some sliding average, you can do whatever you want with your previous data. But as soon as new data arrives, you drop everything and you continue with the statements which come after the receiving of new data. So you receive the new sensor data, then you do a number of things which you are not compromising with in terms of wanting to be interrupted. So everything which is supposed to be mandatory to be processed with that data, you just write immediately after you receive the data from this call statement. You process this data to a first somewhat acceptable level. You produce some initial results to the outside, which means your mandatory part of the job is done. The first level of assurance to the outside is fulfilled. And then you suspend yourself, there's a global loop here, you suspend yourself on waiting for the next data, and while you wait, you can do something else. Yeah?
So I'm just thinking, why don't we just set the get new data to a kind of a drop handler and set it to the highest priority, and we don't need to really avoid so.
This is much more comfortable if you do that. Because if you use an interrupt handler, how do you communicate the data between your main process and your interrupt handler? Shared memory. How do you synchronize your interrupt handler to shared memory?
Once we're in the interrupt handler, the handler just has to control it.
Once you're in your interrupt handler can access the data, which means you violate integrity from the perspective of your process. Because your process can be in the middle of handling this data at the moment. Your interrupt handler just got a free pass from you to access this data anytime it wants. Okay, so you break mutual exclusion. How do you keep the data between your interrupt handler and your main data consistent? Can you make your interrupt handler, for example, wait on a semaphore? So it begins quickly to become complicated. So you're all clear about something like you cannot make an interrupt handler wait on any kind of synchronization primitive. So calling a wait operation, a simple semaphore wait, from within an interrupt handler is not happening. Can anybody explain why not? Why would that be so impossible? Yeah?
Interrupted the other tasks.
Yeah, but why can I not suspend myself as an interrupt handler on the semaphore?
There's no one else is ever going to touch the semaphore because you're the interrupt handler. You have priority.
I could be another interrupt handler to save me.
The
Yeah?
interrupt will become unresponsive. Like you'll be able to trigger that same interrupt again because it's just waiting.
I could make the interrupt handler re-entrant,
Well, I think
call the same interrupt number of times. No, you're overlooking something much more fundamental.
I mean, if you're in the interrupt handler, there shouldn't be anyone else in the critical section.
No. The interrupt handler can strike in the middle of a critical section.
But it's like we're in the protect object, and during that protect procedure is not approved.
So you're hoping that your protected object is disabling interrupts? Possibly.
If you're waiting on a semaphore, there's nothing to reschedule you back when the semaphore is open.
Okay, the semaphore, or whatever synchronization primitive you want, is making your processes wait in a queue, right? They have a process queue associated with a semaphore. Get the point? Process queue, interrupt handler.
So you're not, you have a scheduler which handles this.
You're an interrupt handler.
Yeah.
An interrupt handler is not process. You have nothing to put into that queue. Because if you call a semaphore as a process, you have a process ID. You have a whole block of information which identifies your process. And later on, your scheduler can activate yourself because there is a process here. I can actually reschedule this process. An interrupt handler is not a process. The scheduler has no idea what you are. An interrupt handler is a piece of code. A sequence of statements, a random statement, a sequence of statements. There's nothing you can put into that queue. Leaving your return address here will be utterly confusing for the scheduler. What on earth that's supposed to mean? You cannot suspend an interrupt handler in the same logical context as you can suspend a process. They're completely different entities. Hence, it's hard, and you have to be very careful how you synchronize data between an interrupt handler and a process or task here later. Well, if you format it like that, you don't have these kind of issues because you stay on the level of a task and you can still hard interrupt your task in a fairly controllable way. A lot more controllable than an actual interrupt handler. Okay. Did I convince you somehow? Okay. All right. Cool. Sure.
So if you have some non-interruptible section,
Yeah.
and then you get new data.
So the non-interruptible section would be somewhere, for example, in your while loop here. Yeah.
And then you want to interrupt that.
Mm-hmm.
Where do you wait? Is it after you finish that select statement of the entry?
Yes, I wait until I'm going back out of this non-interruptible section, and immediately after my non-interruptible section completes, I interrupt my abortable section right after that. So if you receive this interrupt while you're in a non-interruptible section, you already know you're doomed. You just have a little bit of extra leeway time until you reach the end of your interruptible section, then you have the guarantee to be chopped off from the CPU.
But you haven't, at that point, you
Yeah.
haven't completed the get new data.
No. You're not becoming schizophrenic, if that's your question here. So the process is still only a single thread operation, even though logically it becomes a bit weird because your process pretends to be able to go through that call, even though in reality, as you just said, it may not be always prepared to directly jump there. So the other process could actually be quite annoyed by, now I finally accept this call. So the professor finally opened the door, but a student has other hobbies at this time, is currently uninterruptible, but I don't have a choice anymore. I have to wait until this non-interruptible section is completed. So I cannot open and close this a number of times. When this call goes through, that means you're also blocking the other side while you're not interruptible here. Yeah?
There's an annoying situation where the professor has the select else.
Yeah.
And he opened the door, and the student is doing this select down board while in his own hobby.
No, a select else is a very different thing.
Yeah, if professor is using select else and he opened the door, seeing the student is doing his hobbies in the
No, that doesn't work. Select else means you're either really available right now, not in the boardable section or anything like that. That doesn't matter in what state you are.
The student is like the calling class is using the select down board.
The other side of getting data.
Yeah.
The other side is in a select or else. Yeah, then you're lost. Then you actually have to go through with the call.
So even if I'm using select and else, I still need to wait for.
Yes. Good question. If you use on the other side the select or else, that means from that perspective it looks like the call is immediately going through, even though the caller is has only actually put his business card into the queue and is not physically there yet. He's still busy with other hobbies, and we have to wait for that then. Good question. Okay. Cool. I think this is as complicated as we got today. You will do a lot of select and aborts in the labs this week. This is also the last lab, which will then qualify you to actually go on hardware. But this is the last lab which I will need to insist that you actually understand what's really going on there and can debug those kind of environments. If you think they're hard to debug, please do all the lab exercises again, because you're still working in a wonderful paradise-style kind of environments compared to working on actual hardware setups. Yes, you do have a GDB on your machine, even on remote hardware. You can still debug and stop and set breakpoints on your actual machine, but this is a real-time system, so this will be a lot harder to debug. Yeah.
When we're running lab machines, is there a way to control time while debugging?
Is there what?
Is there a way to control time while debugging? Can you fake time? Can you pretend that it's some other time? So that, if you have multiple tasks running and you have a breakpoint on one of them, time still keeps ticking.
Yeah.
Even while one of them's frozen. Is there a way to stop that?
Not on your lab machines. In principle, yes. So if you work on a larger emulator environment, you can actually try to stop in an emulated time environment. Yeah. But not for your lab machines. They're just one running on top of a Linux kernel, which doesn't care about these things.
Are there any free or open source software packages we could use with Ada to, when we're say doing some programming for our hardware devices, to run it in an emulator where we're feeding in signals?
The environment which you want for that would be, for example, VxWorks. Which I can get licenses for. VxWorks is, as I said, pretty expensive if you do it industrially, but I can get licenses for that. The alternative which you can play with if you like to, which is open source at the moment, is QNX. QNX is a real-time operating system which is a lot more lightweight than VxWorks. It doesn't give you the same kind of monitoring and control possibilities. It used to be a quite mainstream competitor to VxWorks, and it is still used in industry, and it's openly available. QNX is what you actually see in practice at the moment. If for some bizarre reasons QNX got pretty much the monopoly for a lot of car dashboard interfaces. So if you drive an Audi or any car which has just an LCD display instead of dials on your dashboard these days, what drives this display is almost always QNX, which is quite interesting. So they're taking this at least seriously enough that they have a hard real-time operating system doing these kind of displays. So don't worry, this is not JavaScript or Ruby, which actually moves the needles on your display here. It's a bit more serious. You see QNX in those environments. Don't go too far, because that can actually take a lot of your time if you go into that environment. See first whether you actually have a need to debug on that level. Because you're not making mistakes in the first place, are you? See? Easy. Okay, guys, thanks a lot.